This thing's a fork bomb. So you've got an interesting paradox that one of the main reasons you use recursion is when you recurse twice. Otherwise, you could substitute iteration real easily, or sometimes you need iteration plus a stack. And yet, anytime you call it twice, it's a fork bomb. So now we go to one. Does everybody agree that this is going to be a fork bomb?
Yeah.
So the iteration of exploding is the exponent of 2. First time it goes through, it'll create 2 extra. The second time it goes, them 2 will create 2 more, so it'll be 4. The next time it goes through,
Rabbits.
it'll be 8, 16, 32.
Uh-huh.
It's like, you ever do the math for you get paid 1 penny
Yeah.
for each day? You can't even, average human can't even say the number out loud because they don't know the number of decimal places after you get past 18 or 20.
Yeah, I made a deal like that, and I had to carry my money home in a wheelbarrow. So,
Okay.
and you're looking for a better job, right? I told him, I'll work for a penny today, just double it every day. All right, so anyway, fib traditional exactly matches the mathematical definition. Unfortunately, it fails with large input numbers. And you'll see an example of that. There are several ways to mitigate that problem, but I'd like to point out the beauty of fib traditional, as long as you use small enough numbers, is you instantly, the design is already made for you. If you've taken high school math, you already know the design. You just put the design in your code. You don't have to figure out how to implement the design in your code. It's magic. You say, I proclaim these are the rules, and magically Python takes care of it and gives you the right thing. Now, I've got, since that's a performance problem, I've also coded 3 different ways that you can get around the performance problem. One is fib dictionary, where you don't call Fibonacci, you don't recurse unless you haven't met that number yet. You have a dictionary of all the numbers and their Fibonacci value, and you try to get it from there first. So you're still calling 2 of them, but not very often. There's Fibonacci brute force, which I'll get to later. And there's the one thing I'll say about Fibonacci brute force is it no way looks like the definition. It's basically a recursive way to express an iteration. And then here I just plain out did it iteratively. So now what we're going to do is we're going to count up, count down. We're going to get the factorial of 5. Then we're going to get the Fibonacci traditional of 32, Fibonacci dict of 32, iterative of 32, and brute force of 32. And yeah.
I'm gonna add 1 or 2 more lines. Do another set of dashes out under factorial 5.
And I want to share something too.
Okay, wait a minute. Wait, where's fact? Okay, well,
Okay.
hang on a sec. You're talking faster than I can type. Okay, another set of dashes.
Do 2 yank down line paste. Okay, change that 5 to 364.
Uh-oh, it's read only.
Which one? This one?
Yeah. Instead of 5, which is a very simple low number,
365.
or 364, I think is the actual real thing we want to do. Okay.
All right.
I want to see how bad the difference is in between.
And could we add one other thing before you run
Yeah.
this, if you don't mind? Could we import sys? And then somewhere, can we add a print for sys.get recursion limit? like later on, let's just print it out
Okay, do you want it printed out before any of the other stuff?
wherever. Like, I just want to see the value because there's a get recursion limit and then a set recursion limit.
Okay, sys.get.
Recursion. No, it's all one word jammed together. No snake case. Parentheses. Yeah. And then just do a rapid print around it so we can see the value.
Gotcha.
Yeah, recursion limit. So then that way, if you need to change it, and there's certain cases where you might need to change it. You know, if you need to just.
Well, I can guarantee you with the Fibonacci numbers, you can't crank it up high enough. Okay, you just stone can't crank it up high enough. It can use up every last
you already
byte
have
of your
it.
RAM.
You already have it. Oh wait, did you?
I did that.
Oh,
I did both of them.
I was like, did I not see that earlier? Okay, gotcha.
I'm too quick for you, buddy.
I didn't see it. I blinked.
All right, now what we're going to have, we may have a stall after factorial 5, although I don't think so. And factorial 5, as I remember, is what, 630 or something like that. I don't know.
The fifth digit? No, it's not that. Not that high. 0, 1, 2.
Let's see.
3. Yeah, it should be 3, right? If you start at
Factorial?
0.
No,
Oh,
wait a minute.
factorial. I'm sorry.
1,
Never mind.
2, 6, 24,
Oppo print
60.
instance of DC and do the math.
All right. Oh, the other thing I want to tell you is I want you to notice, actually, wait a minute. I'm going to do this first. The reason I'm going to do it first is I want you to fully see and appreciate the stall that Fib Traditional gives you. Okay. All right, you're going to see your first row of equal signs right away, and then we'll see how long factorial 364 takes. I don't think it's going to take long at all. And I was wrong.
What's the zeros? Total of zeros.
Horrible number.
Okay, so let's see what happened. Wait a minute.
What's all the 1,001 to 10 stuff? You're supposed to start out with.
Yeah, you know, this thing did.
Oh, that's
Oh,
recursion.
okay, the recursion limit.
Yeah, we should have put another thing around it. But yeah, that's the recursion limit. So that's what keeps it from doing the fork bomb you were saying. But if you need to get around it, you know, because 1,000 could be low for your application. Then what you
Okay,
can
let's
do
do this again. Hang on a sec.
is just put a set recursion.
Well,
I mean, that's how you
wait,
change it.
first of all, let's do this again now that we know what's what. Okay, so we're going to get a line of equal signs and then the factorial, then count up, count down, etc. So let's see how long it takes to get that first huge number. Wow. Look how, did you see how long it stalled after the 120?
Mm-hmm.
Let's do that again. Okay, so the thing after the 120 was the traditional Fibonacci. The other Fibonacci's I wrote did not have that problem at all. They happened instantly. Now let's see what they were. All right. Fib dictionary, what I do is every time I pass a dictionary. As a matter of fact, I'm pretty sure the very first time I passed in an empty dictionary. Okay, and then it keeps adding to that dictionary. All right, if the stop case is if num equals 2 is less than 2, return 1. You got to make sure you get there. Okay, if num minus 2 is in the dictionary, meaning if it's a key in the dictionary, then you go ahead and you say n2 equals N2 is going to be one of the two, is going to be the smaller of the two numbers you add up. N2 equals dic num minus 2. You didn't have to recurse. You already had it saved up. Else, N2 equals fib dic. You do recurse, okay? Same thing with num minus 1. If it's key in the dictionary, you just get it. Otherwise, you find it with Fibonacci, with recursion. Then you say new fib equals N2 plus N1. Dictionary of num equals new fib. So now that's available for things that follow, and then you return new fib. And it works like lightning. It's still doubly recursive, I think. I could be wrong. But it does it so rarely that it's not really a problem. Also, you know, I don't think it is doubly recursive because I think num minus 2 is always going to be in the dictionary.
Well, do you want to comment why you have a dictionary?
It's as a cache to save up numbers so that I don't have to recurse to get them. Or do you mean why I used a dictionary instead of something else?
No, that's perfect. I just wanted to, because, you know, I mean, yeah, it's caching. So you don't have, exponential performance. You know, it's you don't want that.
So basically it does
you've already
double
computed.
calculations, it just doesn't do it at the same time, because one set of if-else's runs before the second set of if-else's. So even though you may recurse twice, right, dropping from the top of the depth to the bottom of the return.
But most of the time, you're not going to recurse twice because most of the time,
Yeah, because it takes the other.
one of them, at least one of them is going to be already there in the dictionary.
Okay, I got you, but the whole idea is it does less because of the if-else's. Already knows the answer, it doesn't have to.
If it already knows the answer, it's not going to recurse to look it up. And if it doesn't recurse, that's that much less of a fork bomb you have. All right, now let's look at fib brute force. Remember I said in the very beginning, I said the most general definition of recursion is that it calls itself. Another thing that a lot of people look for, and by the way, there are a lot of people who are a hell of a lot more adept with recursion than I am. What they look for is the ability to structure the recursion in a way that magic happens. So that all you do is declare the rules and bang, the right answer just happens. Now, this fib brute force is an example of not doing that. What I did here is I'm passing the last two numbers you found. And one handy thing about Python is you can use default values for those numbers. So I can call this thing the first time with fib 100 or whatever, and it'll just say fib brute force 100, 1, 1. But then from then on, when I call it with three arguments, it'll work. Okay, so if number is less than 2, I go ahead and call fib brute force with num minus 1. I decrement the number once, and I send it with A1, which at this point is the lowest number, and A2 plus A1, which is now the current number. Or else, if it's not greater than 2, I just return A2 plus A1, and I don't recurse at all. And that's your stop case. Well, I mean, this is really the same logic you use in iteration, isn't it? It's really not a whole lot different. It's not the same mindset as the traditional one I did. But, you know, it gets the job done.
Will you be able to share this code on your GitHub?
Yeah, I was about to say, it'd be easier to follow, because I'm typing it, but it'd be easier to follow it if I had a.
I don't remember my password to the GitHub.
You can post it when you get home.
Or like the event, info or something.
Yeah.
In the what?
So like in the event info, like for next time.
Yeah, I'll make sure you guys have this code tomorrow.
Okay, cool. Yeah, and we can send it out on the email and the GitHubs or however you want it. That's fine. Cool. All right.
Okay, I don't see any reason to discuss fib iter. It's just, it's how your average C program, your average Perl program, your average Python programmer would do it when he or she heard about this.
Yeah. Because then you don't have problems with the stack.
Yeah. Okay, now everything I've showed you so far is kind of contrived. I've tried. This is the crap they show you in the textbook when they get to iterate to recursion. And the reason they show it to you is because it kind of sort of gives you the idea, especially this one right here. I mean, this pretty much, that is the heart and soul of recursion, and it's just too bad that in real life in Python it doesn't work. You did see the 2-second delay just to count up the 30-second one. When you get up to 40, it breaks. Actually, it doesn't. It delays like hours.
Okay.
Then, 100 it would break, but not for hours. All right, so there are certain situations where you're dead meat if you don't use recursion. The one that comes to my mind is dealing with trees. Have all of you dealt with a data structure that's a tree, and it's big and it's wide and it's branching, and you have to deal with that tree?
Shake the tree.
Huh?
You shake the tree.
You shake the tree. How many of you have ever had to deal with a DOM object? Basically, a DOM is typical of these things. You have a parent pointer, maybe. You have a left sibling, a right sibling, a left sibling, first child and a last child.
Mm-hmm.
And then you keep tacking on more and more and more of these things. You get this huge tree.
Is a heap sorted, tree sorted?
I don't know.
Yes.
Okay, that's about the only time I've dealt with trees.
Yeah, that's.
In my early Pascal days, I did the examples in the book, and there was the source code for the different types of sorts and played with those.
A quick sort is recursive, but it has nothing to do with trees.
That's correct. Quick
Yeah.
sort is recursive. That's the time I played with recursion.
Yeah.
Okay. There are other situations that call for recursion. Trial and error. Let's say you does any of you remember back when screens were 80 characters by 24 lines? You could actually make a maze back then by just putting in characters in various places and having the guy start one place and get to the other. If you want to run that maze, you're going to do recursion. And specifically, the recursion you're going to do is the following. The recursive subroutine is going to be make one move. It's going to return true or false, or success or failure. Okay? And it's going to do the following. Go left, go straight, go right. And then if you go left, you're now at that position. And you say, go left, go straight, go right. And you keep on going until you until you can't move. And then you report failure. You say, hey, guy who called me, sorry, failure, sorry, failure, sorry, failure, sorry, failure, all the way back. If that was a left, now this guy goes center, or it goes straight ahead. If that was a left, if that was a failure, now he goes right. If that was a failure, he said, whoops, sorry, I messed up. I'm returning to the guy who called me. And effectively, he walks back where he'd been already. That's how you run a maze. It's called a backtracking algorithm. I dare anybody to do that iteratively. And yeah, it worked pretty fast on my old 286. As a matter of fact, I did it in Turbo Pascal. I had to slow it down so you could actually see it. Because if I didn't slow it down, it was like, One day, it was about that same time, it was in the 80s. I don't ever do this, guys. How many of you are contractors or have been?
For what?
Programming. You know, have code will travel. Okay, well, I was a contractor. And I had like, you know, every week I forgot to submit invoices or I don't know, but I had to reconcile about 5 checks with about 8 weeks invoices. And I had to find a combination that worked. And I couldn't do that. So I had Turbo Pascal, right? I wrote a backtracking algorithm that it basically said, hey, if I'm here, is there any way forward in any direction that can deliver me a match between these invoices and these weeks and these checks? And I set it going, and it wasn't as fast as my maze. I went out roller skating. I came back an hour and a half later, and the exact correspondence between the checks and the invoices was sitting right there and proved that, yes, they had paid me the right amount. Because, I mean, when you screw up like that, you really don't want to call your client and say, which invoices is this for? You're supposed to know. Okay, trees, trial and error. What are some other cases where recursion's just the obvious thing? Yeah, I can't think of one either, but you know, there's a guy I wanted to have here, but he's in Texas right now. He's an expert on recursion, and he could have turned this whole thing around. Do you know that game that they give you at IHOP where it has a triangle that takes 10 pegs?
Cracker Barrel, yeah.
It's a Cracker Barrel?
It's like an intelligence tester thing, yeah.
Yeah. Well, you know, I opened my mouth on GoLug and said I was going to program that thing. Well, I mean, I programmed a maze, right? I programmed tic-tac-toe. What the hell? I'm just getting messed up and messed up and messed up. And then this guy, his name is Barry Fishman. He emails, oh, here it is. And he had done it in like 40 minutes in Lisp.
Lisp, wow.
Yeah, well, it's recursive. By its very nature, it's recursive. And that's a recursive problem because basically I'm pretty sure what he did is he just trial and errored every single move with what would result from that move and just kept going on. The beauty of recursion is when you're dealing with iteration, you're thinking, yeah, but what happens in this case? Well, what happens in this case? Oh my God, I'm going nuts. When you deal with recursion in a problem that requires recursion, you go, okay, here are the basics. And for anything else, I'm just going to kick the can to the guy I call. And you would be surprised how often that works if you do it right. And it ends up looking like like the subroutine did magic. Now I'm going to show you the first. Oh, one other thing. Why even use data that looks like a tree? Why in the world would you do that?
Well, in the heap sort, which was a tree, it reduced the number of compares you had to do as opposed to brute forcing a bubble sort.
Yeah, or something like a linked list. Okay, that's one reason you'd use trees. What are some other reasons? How often in real life, I think everybody here is over 20 years old. Remember back 20 years ago when there was such a thing as real life?
What are we living now?
Facebook.
Oh.
Think of how often hierarchies popped up. There's the hierarchy at work, who works, who reports to whom. There's the hierarchy in your car. Your engine is part of your car. Your water pump is part of your engine. Your impeller is part of your water pump. Menus, which if we get to it, I'm going to show you some code that's from UMenu. Menus are hierarchies. What are some other hierarchies we see just pop out of everyday stuff? Political campaign. You've got the candidate. You've got those few people he or she communicates with. You have a state organization. They have county organizations, on and on and on, right down to one guy who's in charge of 5 people who walk around getting signatures. Some other hierarchies that just happen in normal life. Come on, you can think of them.
Phone trees, I guess.
Palm trees?
Phone trees.
I don't know what that is.
Like you press 5 to get to this menu, then you press 2 to get to another menu, and you press 3 to.
Phone trees. Exactly. I dare you to do that any other way except with a node tree. Well, I suppose you could do it recursively without the data, having the data. Oh, that would be horrible. What else? What are some other hierarchies that pop up every day?
XML.
XML. Well, XML is a tree. It's DOM.
Yeah.
And everything thank you. An average document. You have paragraphs that are split into things with this kind of style and that kind of style, and all those are split into letters.
Yeah.
And then at a higher thing, you have containers, you have span and div, you have body, you have the whole HTML thing. Yeah. So XML, HTML, DOM. They're
Graphic stuff is this way too.
Oh, that's a good point.
I got a book on Visio because I'm a student now. I get a thing of Visio, and I think there's more documentation on Visio than there is Inkscape initially. So if I burn through 1 or 2 books on Visio and sees what it'll draw, I want to use Inkscape, not as an artist. I want to use Inkscape to make computer flowcharts and stuff like that. And from reading the appendix chapter in the book, it appears to be that at the low level that most users don't use Visio, it uses a bunch of spreadsheets, tables, to find all the objects in its parameters or whatever, but it's all linked together. You can use VBA or whatever, but that's the programming language to link all these objects. So by the time I'm done, I might not simply know how to use the Microsoft product. I would know how maybe to write my own Inkscape scripts to make it do more advanced things, since it seems to be all these programs are not documented very well beyond the initial tutorials and the reference thing. There's no in-depth studies on a lot of this stuff.
Okay, so drawings, and especially what do you call it? SVG. Vector drawings are obviously hierarchies.
Yeah.
Every time you group a bunch of things, there's another hierarchy.
Yeah, because the top thing in the Visio is the main object is the document. Under that is basic framework, and then the very primitive objects such as square, polygon, circle, line, dot are all subordinates to, like you say, that part of the image.
Okay. So basically, just to summarize this, a lot of things in the world are hierarchies. If you're doing any kind of data manipulation with hierarchies, you will thank yourself to put that data into a tree type form. And once you have something that's a tree type form, you're probably going to want to attack it recursively. Now here, what I have, this is a tree sort. It's a binary tree sort. A barbaric, brute force, binary tree sort that's here simply to show how you would address things with a tree. This doesn't have any balancing. This doesn't have any of the niceties that would make this a real product. But it does quite nicely show how you can attack a tree. Now with a tree sort, what you do is you dribble in data one piece at a time and store it in the tree. And then at the end, when it's all stored, you walk the tree to get it out in a sorted order. Okay, my data is integers because, I'm just trying to get the point across here, so I'm not going to use something that's going to complicate it. So we have a subroutine called push node. And you pass it a number and a node. The number is the next number you want to store in the tree. Now the deal is, this is pretty cool. Here's the logic of this thing. Let's for the time being stipulate that there are no two numbers the same. I actually arranged for equal numbers here, but let's just say no two numbers are the same. It's easier to understand. A number comes in, right? And you push it onto the very top node. It's called the head. And in the main program, you've made the head be an empty dictionary. And then you push node a number and the empty dictionary. So what's going to happen? The very first time you do it, it's going to say, hey, the node is empty. The dictionary for the node is empty. It has no num key. So I'm going to do this. I'm going to make a node whose num is that number. So what I've just done is I've made my very top node as a dictionary that has one key value pair, and that's a key called NUM and the number. Done. Okay, now that's the end of it, all right? That's not recursive. You've got a loop driving this thing, an iterative loop, handing it one number at a time. And each time it puts that number, it starts at the head node. So the only time you hit, if there's no num in there, is the very first time you put a number in it. From then on, you don't have to worry about that. Now, in the general case, if the number you just send into it is lower than the node's num, then you want to place it down and to the left of the current node, right? If it's bigger, you want to place it down and to the right. There are two possible things that happen. If you do not have a left pointer, an L key in the node, well, then you can just make the L key this number, and you make the node key another node that has this number for its num. That's easy, right? Any fool can do that. Same thing if it's greater than. But what happens if this node has no, if your number is smaller than this node's number, and this node already has a left, an L key value pair? What do you do? Oh my gosh, what do you do? Think of all the details. What do you do? Look at the code. That's all you do. You say, well, hell, I don't know what's going to happen. I'm going to kick the can down the road. I'm going to call myself again. That's all you do. And what happens is this number falls. Have you ever seen these playthings with like a plastic pin on top and 2 plastic pins and 3 plastic pins and 4 plastic pins, and you drop a ball at the top and it goes point, 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 point. You don't know where it's going to go, but you know it's going to end up someplace. It's the same thing with this, because what happens is if your left is already occupied, fine. You call a recursion on that node, and it's either going to have a left or a right, and it's going to keep on going down and down until it finds a final point. Now let me run this program for you. Does anyone have any questions about what I said so far?
So all this does is build a tree. Okay, there's your read tree.
Yeah. Okay, you can safely ignore all this junk because I told you no two numbers will be the same. This junk that I just highlighted handles it when you get 2 of the same number. I shouldn't have even put that in. And then you return the node, and I don't even think that's necessary. No, that's not necessary, because you know how dictionaries are passed by reference? So when you pass a dictionary into a subroutine or into a function, and the function changes it, well, as a side effect, the dictionary is seen from the outside has changed too. It's passed by reference. So you don't even need to return node. All right, so what I did, then I have a read tree thing here. I'll get to that later. My input in sorted order is 42, 22, 77, 33, 99, 41, 23, 90, 50, 9 numbers. I start out with head equals an empty dictionary. And then I say for n equals input, input is the array, head equals push node n, at head. So I want you to understand this part is completely iterative. What's not iterative is each time I do this, push node keeps calling itself until it finishes, and by side effect, head has been changed. Then I'm going to JSON print this thing, and I'm going to say sort keys equals true. The reason I'm doing that, if you notice the way I constructed my 3 key names, they are L, num, and R. And interesting, they occur in just the right order. Left comes before num, num comes before R. So when you look at them in a JSON pretty print, it's going to look pretty much sorted anyway. And then I do a very simple procedure called read tree, which is also recursive. So let's come over here. Tree sort.py. All right. So what happened is the function that took in all the numbers stored all the numbers. And okay, the bottom leftmost, try to twist this thing 90 degrees to really think of it. So this 44 here is your top node if you twist it sideways. All right. So the bottom left L has a number of 22. And then you get a number of 23, 33, 41, 44, 50, 70, etc. So you can see it's kind of stored them in the right order if only you can traverse the tree in that same order. And here's how you traverse the tree in that same order. It's called read tree. And it walks the whole tree. So you start with the head, right? You say read tree head. And I think the head was 44, as I remember. And what you're going to do is walk the tree down left to center to down right, yielding the sort. So on your node, if there's an L key, do a read tree on that node, on the node in the L key. If you can't do that anymore, if you return from that or you can't do it at all, then you print your number. And then if there's an R key in your node, you read tree the R key. Now, can you see this leaves out a lot of detail of walking through that tree? I mean, just try to do this recursively. It would be horrible. But, you know, doing it this way, anything having to do with trees, it just really simplifies it to do it recursively. And so bang, what happens is you got sorted. There are all your numbers. So this is the first example I've shown you that isn't just pure contrived bullshit. You know, when you have to walk a tree, you darn well better use recursion. Now, what time is it?
7:30 almost.
All right.
I've actually got to get going here.
Huh?
I've got to get going here pretty soon.
Okay. Well, you've seen most of it. Let me tell you this one thing. You can simulate recursion by iterating and messing with a stack.
Mm.
You know, if you absolutely hate recursion, you can use a stack.
Okay.
But in most cases, you're going to have a hard life if you do that. You know, for a long time, I figured I'm not going to do recursion. It's too crazy. I'll use a stack. Well, you talk about crazy. When you have to remember where you are on a stack and how many you move up or down, it's an utter horror.
Right, pulling and pushing and all that, trying to keep track of it.
Yeah, it gets real bad. The other thing I'll tell you, which we're going to get to later, is what I generally do if I'm dealing with a tree. Instead of doing one recursive subroutine that just does everything I need to do with the tree, I'll make a series of tree walking recursive subroutines that do one thing and do it well and call them in order. Is that as efficient as making one function that did it all? No. Do I have the brains to design the thing to do it all? No. So I just do one thing at a time. I have, in my U-menu thing, I have a thing that goes through all your children, and if the child is called data, I treat it specially. Well, I don't do that when I'm putting the tree together. I put the tree together as if data is just another child. And then I have a tree walker that when I get to something called data, I call a subroutine to change what it is. I move it to a dictionary and zap it from the list of children. It works out pretty well. I think I've told you basically the essence of what we're doing here. The rest is just going to be looking at some code. Anyone have any questions? Okay, I have this program called U-menu, which it's just a menu. And it's a menu that's defined. Let me show you how it's defined. JP, it's been great meeting
Yeah,
you.
thank you. I appreciate all wisdom.
I have lots of fun.
Take care. It's nice meeting you.
See you guys.
Bye-bye. Okay, so where's home? SLit. U-menu. Come on. U-menu here. Okay, my top level menu has selections for A, B, C, all the way through Z. Okay?
Mm-hmm.
And the metadata about that top level data is in a directory called data. You notice it's the only directory that isn't a lowercase single letter. So the three pieces of metadata I have about it are menu title, sort, and type. Type is whoa.
Oh, that's nice. I like that.
Yes, thank you.
I like
Well, it's M for menu.
Nice.
Sort, send to, please tell me, gvim. Okay, what this means is take the F selection, put that first, take the X selection and put it last, and all the rest of the selections, put them in alpha order where the dash was. Okay, and then, you know, like let's say that I selected B. Well, B has data with no sub menu items, so this is a command. And the command is specific. Darn it. Send to gvim. Okay, so whatever that thing is, it's n grep umenu sort. All right, anyway, so you see the point. I'm building a tree of menu items, and each menu item, huh?
What's in stop? Because I know what stop does. You got just a single character.
Let's see, I don't remember.
I still think this would be readable if you combine all them files together and not make a subdirectory.
Well, then you'll be glad to know that the code you're seeing converts one of those to this. You get the best of both worlds. Because what you're describing, David, you wanted stop, right?
Yeah.
Oh. Jeez.
You just right-click on it and tell them it's a text file with you.
Not in Roxfiler, it's weird. Okay, now, file stop, send to gvim. It's a T.
For true and false.
Yep.
Oh,
And the default, if it isn't there, the default is false. And you know exactly what it is. It was just a
pause
little
to
different.
continue before you return.
Yeah. Okay, so anyway, David pointed out, and I soon found out, that if you really have to make a whole menu system, you don't want to be using Roxfiler and going in there and dinking with every little thing. It takes lots and lots of time. You want to be able to do it in an outline. All right?
Or I do it in key value pair.
Huh?
I would do it like more of the original menu system, just key value pair. Even though your key value pair had a white space, not a colon or something.
Well, wait a minute. Are you talking about, what we're talking about here is there was a legacy version of umenu.
Yeah, I'm not
Which-
familiar with it that much.
You're lucky. It was good for little tiny menu systems. It sucked for anything big.
Okay.
Are you talking about the MNU files or are you talking about EMDL?
I'm talking about the MNU file, the menu file.
Okay, well, those things were silly to make a big menu with. There was no way to portray a hierarchy with them. It was horrible. But anyway, let me show you what you can do now.
But the hierarchy was the final.
That shit is. Let me show you what you can do now, because you were the only one on earth who used those damn MNU files. All right, so
It's easy to move it to another machine. You just tart up everything and you get, or zip your tart, depending the destination.
you can do that the same with the directories. You could.
Yeah, but you just simply edit them to make a change.
You can now. All right, now watch this. CD, what's it called?
But the original program had node.pm because it was originally written in Python, and that's what you're saying was the definition for your tree functions were defined.
Okay, so what we're going to do is we're going to use dir tree we're going to convert a directory tree to an outline. So dir tree, and the file the root we're going to convert is home slid umenu to menu s. And let me put that in less. Okay, so at the very top is the base directory of the whole menu system. The S that's indented from it is the root menu, and it just goes down from there. And what's interesting, I'm sorry, I had not gone over this since the election.
Yeah, notice that.
Yeah, I'm.
That's why are you sorry?
I never thought this would be seen outside my house. Let's just scroll down a little.
I thought.
That'll show you better go over your stuff before you display it to other people. Okay, so let's find a data with sort in it.
What's that .exe? How do you run an exe?
Oh, I just called something exe. Oh, wait a minute. Okay, see this sort MT PBQ whatever? What my program does is never mind. Okay, anyway.
Because the original program, it was just how it was listed in the menu file. You wanted the Z option at the top of the list, not alphabetic. You simply sorted that text.
Wait, let's not even confuse the issue with that ancient thing. That thing was weird. Okay, so basically what this outline does is it defines an entire menu hierarchy. All right? Now, the one thing, I'm going to try to do a round trip circle with this thing. So what I'm going to do is I'm going to actually write it out. I'll write it out to junk1.mnu. I'll put OTL. gvim junk1.otl. I'm going to change this S to okay, I'm going to change the S to C. Okay? And now what should happen is I should get another hierarchy just like the first one, except the top level will be C. So what I did was I took the existing S directory tree, turned it into an outline.
Do another LS and see if it created a C.
It can't yet. I got to run the program to do that. All I did was take the directory tree and turn it into an outline.
Okay.
Now I say OTL to umenu junk1.otl. And so now we come back here.
An LS and I should see 6 directories instead of 5.
How late are we?
7:37.
Menu, umenu to menu. We've got our C directory. Now watch this, guys. Diff R CS less. And I'm contending most of the differences you're going to see are going to be in sorts, because the outline actually makes a sort thing that implies the exact order in the outline.
Yeah.
An outline can have an order because it's sequential, or it has part of it is a sequential nature. Your directories in a tree cannot have an order. I mean, what are you going to sort them on? You know, I know.
I could sort it on title.
Well, you might see the point is different people want it sorted on different things. Anyway, watch this. So I'm doing a diff. Okay, well, I had a .get in here and I shouldn't have had it at all. Okay, now you see up here this paste in custody name and last whatever. I can't see any difference in those two. I don't know what it's seeing. Okay, sort, menu, title, they look the same. Basically, they look the same. Now, watch this. We're going to take the newly created C and we're going to make it into jump2.otl. All right, you with me so far? Oh. All right, let me go back to recurse. Oh, CD bserve. Okay, now we should have jump2.otl. There is a difference. Okay, now we're going to use jump2 to make a D. Oh, not before we change jump2.
So what's the 3s, 4s, and 5s at the beginning of that file? Each line. Edit it again.
Oh, what do you mean? You mean that's just part of diff. Okay, so direct, I want. Okay, jump2 should give us a D. Okay, CD, umenu to diff-r cd less. Nothing, man. Round friggin' trip.
Okay, I have all my menus set up.
Okay, wait, let me just in the last 5 minutes show you how that got done, okay? All right, so CD recurse bserve gvim otl to. All right, so let's take a look. This is the thing that takes an outline and converts it to a directory tree. And if we come to the very bottom of this thing, we see that what we do, menu, okay, I handle the command line arguments, fine. I have a object called lines, which just gives me the ability to take all the lines for the outline and have them in an array and give them an additional metadata like indentation, like what the line number was in the raw data, because I'm subtracting any lines that are comments or blank, stuff like that. So then the base directory, which is the directory under which all my menus are, and then
Don't worry, keep going.
And the root letter, which is the C or D or S, equals get initial information in the lines. Nothing to see there. Now here's where we start getting recursive. tree equals make initial tree lines current. That means you already read 2 lines out of this thing, so it gives you the same line you read last, and the lines object. The whole purpose of the lines object is to sort of give you a way to sequentially read lines out of this thing no matter where you are. So we want to go to make initial tree. And it's pretty short. Okay, I handled the level. I handled some break logic with pre-level and next level, because see, you're going to recurse when your level of indentation gets greater. That's when you're going to recurse. Think of an outline. It really is just a hierarchy, and going more to the right in an outline is like going to a deeper level in a tree. And the tree has to reflect the levels of the outline. So I'm doing one of those priming reads with a read at the bottom of the loop, and the reason I'm doing that is because forget it, I just did. All right, while you have more lines to read, you calculate the level. If this level is an indentation of greater than 1, if there's a double indent, blow it off, man, you got a bad outline. Or else, if it's a single indent, well, then you have to recurse. So you go node, children, append, because every node has an element called children, append, make initial tree recursive line. So basically, we call ourselves again. Except that wasn't. Actually, this is the one I used and it's iterative. So let's go on. I didn't get that to work. All right, so the next thing we do after we make the initial tree is we do move data. And this is a good example of my
Little g.
Okay, move data. So now we've got this whole tree that represents the outline where stuff under data is no different than anything else. So what we're going to do is move data from the children to its own dictionary. All right, so data rex equals 0 equals an empty array. Sort equals an empty array. We're also, while we're going through all this stuff, we're going to load up a sort string for the menu to use. Okay, so now what we're going to do, we're going to go through this node's children one by one, and if the node text says data, then we're going to append that to the data rex array. The reason we're doing that, if you have 2 datas in there, it's an error and you're going to blow off. If you have 0, it's an error. All right, so then, or else we just record the letter for sorting and go on. Now we come down here. If the length of data rex is 1, then we're going to massage.
Okay, in the source string.
Oh, we're just going to do some mumbo jumbo. Forget it.
Okay, you got a source string, right? That's all your letters.
Listen, I don't have time to explain all that, but basically what you're going to do is you're going to come down here and you're going to, with this data rdict, you're going to turn the data into something that really is data instead of just a hierarchy. You're going to turn it into what it should be. Now, if the number of children is greater than 0, you sort it or something. I don't know. But if you've got more than 1 data records, you blow it off. Now, the very bottom is where the action is. Now, for each child that this node has, move data on that child. So I had quite a bit of stuff going on here, but basically what I just made sure that whatever I did up there, I can do on all my children. And really that, that isn't something you're going to write in an hour, but it is something that's fairly simple once you get it done. And what I just did is I took that whole tree, walked through the whole tree, and took everything named data and everything under it, changed it to be metadata, and put it in a data dictionary instead of in the children array for the node it belonged to. Okay, right after that, after I moved the data, I checked subtree names. I wanted to make sure that anything in there was called either data or had a single letter lowercase. So check. All right, here it is. Well, this is pretty easy. Okay, if this node does not have a valid letter, you exit. Otherwise, you do the same thing for all the children. Okay, coming back down here, assign directories. This is where we add a few keys to the node, and those keys are directories. Okay, well, here it is. So you make a relative directory, a parent directory, an absolute directory, and a base directory. And then at the bottom, once again, for child and node children, assign directories, blah, blah, blah. Come down here. Okay, we've assigned directories. The last thing is write tree to disk. All right, so what we do, we've got to make a directory for this node. And we fiddle around with directories.
Very nice octal.
Where?
No, I'm saying very nice octal.
Oh, that 075, blah, blah, blah.
Very good.
Thank you.
Is that how you prefix it?
Yep. Other languages do it similarly.
I didn't know the O one.
Okay, so now you're going through data, and data has keys, has key value pairs. 90% of the time, the key should be, well, 100% of the time, the key is a file name and the value is contents. Usually the value is one line, it can be more. So we're going to go for every key in data. You find the value, you make a file name out of the value, out of the key. You open the file. If the type is a list, then you write all the lines to it. Otherwise, if it's not a list, you write the value, you close. Then, right at the bottom, same thing as always. For child in node children, do the same damn thing. So I had, to do quite a bit of work, I had four fairly simple walkers that just walked the tree and did the same thing everywhere it landed. And it's now
7 to 8.
Yeah, so we're done.
So you got one that reads the old menu files to build the outlines?
No, but I'll tell you something. Well, wait a minute. The old, what you think of as the old menu files, nobody uses those. I haven't used them in the 21st century. No one uses them. Is there anything I can do besides close this? Do I need?
Yeah, just close it all. It didn't work, unfortunately. I do have an audio recording of it, but yeah, I was really disappointed that I didn't get that screen session because that would have been awesome.
Okay, so
So what do we want to do? I missed the first 40 minutes with the audio. Like I do have it recorded. Do we want to keep it?
yeah,
Even if we missed 40 minutes?
4-0.
4-0. Yeah, I know. And plus no screen session. So I'm kind of, yeah, I think I'll just dump it. But that's really unfortunate because I wanted to get that. Google really failed me twice. They decided to move the Google Hangouts on Air to somewhere in YouTube Live, and they put it under Other, and it was not obvious. So it took me 40 minutes to figure that out. Well, 39 minutes, but anyway.
Okay, who knows?